Hello and welcome to another topic in chemistry. Our focus today is an introduction about acids and bases in chemistry. If you are watching this video when it was assigned for try 3, go ahead and start setting up your focus notes. The essential question that we will be answering today is, what are the definition and properties for both acids and bases, and what is the pH scale related to acids and bases? Go ahead and set up your focus notes. Pause the video if you need more time. If you're watching this video at any other time for any other reason, I welcome you and I'm excited to talk about chemistry with you. Let's get into it. So let's talk about properties. So remember, property in the chemistry world is a description. Think of it like an adjective. So the first property is that what we're talking about, these acids and bases are all aqueous solutions, meaning that you have taken some type of solute that has a definition of an acid and you've mixed it with water to create a solution of some concentration. And then same with base. So you have taken some solute of a base and you have mixed it with water to create some concentration of an aqueous solution. So that's the first thing to acknowledge. By definition, acids and bases are not always aqueous solutions, but that is what our focus is in this unit. All right, let's talk about acids first. So the general definition of an acid is a compound that produces H plus, so a hydrogen ion, when dissolved in water. So the idea here is that there are things floating around in that solution, but the thing that makes it an acid is the H plus. This is one general definition of an acid. If you take more advanced courses, you'll learn different definitions, but this is one that works very, very well. Some of the properties are acids are the things that have a sour taste. So think of citrus fruits. They have an acid in them. There's also like something like pickles has vinegar, or cucumbers that are soaked in vinegar gives it a sour taste. That's because vinegar is an acid. So these things, if you can eat them safely and they taste sour, or tangy, it's because that's some type of acid in them. If you take an acid and you react it with the carbonate ion, sometimes found in rocks, but it could be found anywhere, you will produce carbon dioxide gas. So you would see that fizzing. So one example is a very popular kid demo is baking soda and vinegar. You mix them together, you get that kind of volcano explosion, right? So that fizzing over, well, that's because vinegar is an acid and baking soda is sodium bicarbonate. So it's got the carbonate ion in it. So the acid is able to break apart and then you end up with just the CO2 gas. So that's where you get all of those bubbles. So that's something. So if you're testing for acids, you could take sodium bicarbonate or baking sodium, or like carbonate that's in different rocks and minerals, so naturally in the world. And so when acids mix with them, they will bubble, they will fizz because they're producing CO2. Another test you can do is that many metals react with acids to produce H2 gas, so hydrogen gas. Well, that makes sense because we know that acids have H's in them. So what can happen is, now it depends on the reactivity of it. So think of that like activity series. So for example, copper in acid, we don't really see much of a change. Sodium actually in acid actually produces a flame, and that's because this acid would be an aqueous solution and sodium will do that with just water. And then you can see that lead has a little bit of reaction, magnesium, iron. So it does depend on how reactive the element is and how easily it can exchange or move its valence electrons. But in general, acids will react with metals and they will produce hydrogen gas. Okay, so those are some properties of acids. Let's learn a couple more. Acid solutions will conduct electricity because that H plus, which is positive, can attract the negative current, because remember that electricity is made of electrons, which are negative. So that makes sense. So it can either conduct it really, really well, like there's lots of ions floating around, like every ion breaks apart. So every H breaks off of the chemical. So there's lots of H's floating around, strong. Or there can just be some H's that break off, because notice here, there's some H's that are just part of the polyatomic ion. It's just an H plus that broke out. So then you don't have as many ions. So then that would be a weaker attraction. But because there's H plus present, that can attract the negative electricity current. And then the other reason that we sometimes talk about acids, or the connection you might have in your world, is about acid rain, like the problem of possible acid rain. So what happens is different pollutants, sulfur compounds, nitrogen pollutants, get into the air from factories, from cars, from different places, and then they react, or they connect or react with water vapor in the air, and then that can fall as acid rain. And so that's an issue if it happens a lot, if it happens fast, because remember what we just talked about, that acid can wear away different minerals and rocks and metals. So if you live in a place where there's acid rain as a problem, that can affect structures and your vehicles, even things like that. But then it also can be a problem for animals and plants. Now, if it happens slow enough, the animals and plants can adapt to it. But if it happens fast, that can be a too high of an acid content, and that can damage plant cells and be bad for fish and other animals trying to drink that acid rain. That can be a problem for them. So acid rain as a problem, definitely something we think about. In different areas of the world, it's a bigger problem than others, just depending on how many factories, especially like burning fossil fuels and things, can produce that, and different other pollutants. So anyway, but another connection to our world. And we're going to actually talk later about what we do with this problem. So stay tuned for another video. Let's talk about bases next. So the general definition of bases is that it's a compound that produces an OH minus, or it's a compound that can accept an H plus. So there's some part of it that would be attracted to an H plus. Again, there's other definitions of bases, but these two are pretty good ones in terms of thinking about any type of base we see out in the world. So bases are things, if acids are sour, bases are things that have a bitter taste. So that thing that kind of makes you like stick out your tongue, right? Or your tongue feels kind of like dried up. Like that's a bitter taste. And they also will react with acids. So acids and base react with each other. And when you do that, you produce water and some type of salt. And the reason you end up with salt is because you've got an H. Remember, we said that's a definition of acid. And OH, we just said, is the definition of base. So HOH is water. Well, this H had to have broken off of something negative, and this OH had to break off from something positive. So that negative and positive left over will make an ionic compound, and that will be some type of salt. So that's where that comes from. And we're going to talk a lot more about this, again, later this unit, about acids and bases. But that's one of the factors of things we say that bases and acids have in common. Another thing is that bases will also conduct electricity, because remember we said that the general definition of a base is that it breaks off an OH. Well, if it breaks off an OH minus, it had to be a positive that's floating around there, and that positive thing that broke off from the OH minus, that can attract the negative electricity. So conducting electricity is not something that makes an acid and a base different from each other, something they both actually have in common, because there's ions floating around. And then the other thing is that bases would feel slippery. Acids and bases can both burn skin cells, but feel like it's burning, but it's a little bit different. So bases feel slippery. This is a fun little side story. So you might know that your skin is made of cells. If you think back to your bio days, a super simple version of a cell. Well, it turns out that this membrane on the outside is made of a type of fat. That's the type of molecule that creates that membrane. And what happens is that bases can dissolve or break down that fat membrane. And what happens is all the stuff inside oozes out. So like when you are washing your hands, if your hands still feel slippery after you're done washing them, it's because that cell ooze is on your skin, because the base from the soap has broken down that cell membrane, and you actually have cell ooze on the outside of your hands. Now, there are also some soaps that have lotions and oils in them to help make your skin feel soft. So soft and slippery are different things. But if you just feel slippery, you need to go back and finish washing off the cell ooze from your hand. So this usually doesn't hurt us because the outer layer of our skin cell is dead anyway. But if you use a base that has a lot of base compounds in it. So if it's considered a strong base or a high concentration base, what it can do is it can eat through more and more layers of your skin and cells, and that could be very, very dangerous, very painful. So the reason I bring this up is that a lot of people, know that, oh, be careful with acids. Acids can burn your skin. It's really dangerous. But bases can be very dangerous as well because what they can do to living cells. So just a note about acids and bases, both of them in the wrong concentrations and the wrong setting can be very dangerous. We got to be careful with both of them. All right. One last thing I want to talk about in related to acids and bases, just kind of thinking about describing words, is I want to talk about what does it mean to have a strong acid and a strong base. So what this means is if you take your acid solute and put it in water, all the acid pieces break off or all the base pieces break off. So that means that, so for acids, that'd be H pluses. So every H plus that's available has broken off, or every OH minus that is available has broken off. And so that's what we mean by that. So see how in this one, a strong acid. So we're saying that the little white circles are the hydrogen, and then whatever it broke off of is this red dot. So see how when I put them in here, there's a red and a white, a red and a white, and a red and a white. Inside here, every red and white are separated. So you end up with a lot more H pluses floating around. In a weak acid, notice that sometimes they stay together, the red and the white. So sometimes the H's break off, but other times they don't. So that would be true for bases as well, using the same idea that in a strong base, every part breaks off. All the ions are floating around. That's possible. In a weak base, only sometimes does it break off. And that's important because that has to do with how acidic or basic something is. But what I want to clarify is it doesn't mean it has a high concentration. So you think concentration like molarity. So you could have like a 0.01 molarity solution of a strong acid. So even though it's a lower concentration of moles per liter, every H possible has broken off. So strong acid just means that the available ions, every available ion has broken off. It doesn't automatically mean that there's a lot of moles per liter of that ion. It just means every ion possible has broken off. So something to clarify about that. So strong acids and strong bases. All right. One last thing in this section, I want to just talk about a list of strong acids and strong bases, but absolutely you don't have to write these down. So some strong acids, some that you might have heard about, HCl is the hydrochloric acid in our stomach, sulfuric acid, that's in lots of batteries, so maybe you've heard of those, and then you can see the other ones. And then strong bases, so sodium hydroxide is something we use a lot in labs, and you can notice that every single one of these has an OH, every single one of these acids has an H. But what you might want to also notice is, what do you notice about these circled examples? Do you notice something? Yeah, they have two of them. And the reason that matters is that since this is a strong acid, if you dissolve this in water, you get twice as many H's floating around. And that's going to be important for pH, which we're going to talk about in a little bit. Or you get twice as many OH's floating around. And that's a big deal in terms of how many H's are present to make it have base properties or acid properties. Okay, go ahead and pause the video and write a level 1 question. Kind of think about the properties of acids and bases, definitions of acids and bases. Write kind of a straightforward kind of question. Take a little break. Come back when you're ready. Okay, so the next thing I want to talk about, I want to talk a little bit more about water. So water, like all particles, the kinetic theory says that particles are always moving. So water is always in motion. So imagine this was a sample of water. Every person would represent a water molecule, and it would be colliding with each other. So if this was a crowd of people and you're trying to move through it, you're going to bump into things. So because water is always colliding with itself, it does something called self-ionization. So self means it does it on its own. Ion means it's turning into, or ization means the process of turning into an ion. So what that means, it means if you have at least 2 water molecules, they will give ions, 2 ions. So that is also known as the dissociation of water. So dissociation also means the same as ionization. So it's splitting apart into ions. So water splits up. Now, the reason that's interesting is because that means that water sometimes can produce pluses and sometimes minuses. And that's what I want to show you next. So there's two different ways we can show that dissociation of water, how water splits up from itself to create ions. So here's a water molecule. You can see the lone pairs and the covalent bonds. Here's another water molecule. When these two things bump into each other, this hydrogen can be attracted to this pair of lone electrons, and they can actually make an attraction and they can make a bond. So this H just got ripped off because it was attracted to this lone pair, and then that left an OH left over. But this is an extra H, and H's are positive. So now this whole particle has a positive charge. This whole particle has a negative charge. So this is known as the hydronium ion, which if you read about chemistry and science stuff, you might have heard of that sometime. It's really just water with an extra H, meaning it's water with a positive charge. And then the hydroxide ion, we've used that in different other places, OH with a -1. So those are two ions that can be formed when water bumps into itself. But this back and forth arrow means that as soon as this happens, this then bumps into itself, and then the H goes back and attracts to this, and then you get this again. And then this bumps into each other, and you get this again. And it keeps going back and forth and back and forth. So generally, the overall number of positive pieces, negative pieces, and neutral pieces all balance itself out, which is why we say that water doesn't conduct electricity, because this is happening so fast, we never really notice a positive charge for very long or a negative charge for very long. The shortcut way of showing this is take one water molecule, split it into an H plus and an OH minus. Because remember, water is really written like this, HOH. So if the H rips off, you have a plus charge, and the OH minus then would be left over. Realize that these two things are the exact same thing. So an H plus or H3O plus, it's the exact same information. This is just the shortcut. So the self-ionization of water, where water can be splitting up into ions, and so you can see that, well, wait, this would fit the definition of an acid. This would fit the definition of a base, but they're happening back and forth so much that everything kind of balances out. So if you have a sample of pure water, you will have some amount of H plus. This bracket means molarity. So this means the concentration of H plus in molarity is 1.0 times 10 to the -7 molarity, a very, very, very small number. The OH minus concentration in molarity is also 1.0 times 10 to the -7 molarity. Because remember, if you have an H plus, it broke off of an OH minus. So they will always balance each other, and they will be at the same concentration. Now, this is going to lead into our next topic about pH. So pause here for now. Just process this part about the dissociation of water and the concentration of H and OH. So write a level 2 kind of question. Pause the video, take a little moment to kind of think about that. Come on back when you're ready. All right, let's finish this off. So talking a little bit more about H plus and OH minuses. So if we have an acid, remember that definition is because H pluses are floating around. If we have a base, that's because by definition OH minuses are floating around. So if I have an acid, if I compare my amount of H concentration in molarity to my amount of OH minus concentration in molarity, remember that's what this bracket means, acids will have a higher H plus concentration. So these two things start as neutral when they're in water, because remember, acids and bases are aqueous solutions. So then whatever I pour into the water, I've added more H pluses. So then overall, it's not balanced anymore. I have more H's than normal. So then now this would be considered an acid. If it's neutral, what do you think this will be? Think about it before I show you. Yeah, it'll be the same. So this is why we say water is neutral, because the H pluses and the OH minus concentrations balance each other out. The moles per liter of H plus is equal to the moles per liter of OH minus. And then for bases, which one will I have more of? Can you figure it out? Yeah, I'll have more OH minuses. So I started with something neutral, water, my H2O, and then I poured something into it that produced OH minuses. So then I have more OH minuses than neutral, so then that makes it a base. And then its indicators are chemicals that react with either H pluses or OH minuses. So it's a chemical reaction that changes color, and it indicates or tells us if we have an acid or a base. So that was like that demo. So if you're watching this video from class, you'll see that that was why we got different colors. I did a demo like this. So the reason we got different colors is this indicator was reacting with the H's or the OH's in the solution to produce a color, and then it tells me acid or base. So in this example, blues were bases, and then the reddish oranges were acids, and then the yellow was neutral. So different colors because the chemical of the indicator is reacting with different chemicals to change color, and then that tells us if it's an acid or a base. All right, so then that connects me now to the pH concept, which was developed by Soren Sorensen, who was a Danish chemist. This is the early 1900s. And what he came up with after doing a bunch of work and experiments and some math stuff, he said that let's have a scale that measures how acidic or not acidic something is. And it's called the pH scale. And it's based on the negative log of the molarity of the H pluses. Turns out there's also a pOH scale. You might not have heard of this one, but it's the same math, the negative log of the OH minus concentration. Well, it turns out that if you multiply the H plus concentration times the OH minus concentration, that will equal 1.0 times 10 to the negative 14. Because remember what I showed you earlier, H pluses, when they're neutral, is 1 times 10 to the negative 7, and OH minus is 1 times 10 to the negative 7. So 1 times 10 to the negative 7 times 1 times 10 to the negative 7 is 1 times 10 to the negative 14. So then if you have a pH and a pOH, that will add up to 14. Why? Because those of you that are familiar with calculus know that log values are really focused on the power of 10. And since it's negative log, then the p values add up to 14. And you could calculate this. So if I know the H plus concentration, like if I know the molarity of my H plus, I can calculate the pH. I take the negative log of this number, that would give me pH, or I could do the opposite function. If I know the pH, I could measure and actually calculate how many moles per liter of acid I have. So these are equations we can actually use. For now, we're mostly I want to show you where the pH value comes from, and we'll just mostly talk about it qualitatively, knowing it's based on math, it's based on numbers, so it has a good solid background, even though we generally just say, well, 14 is the highest pH that we have, but it's based on this information. So let's make a connection to that. So you maybe have seen pH paper before. Maybe you have a water, like a fish tank at home, or you've maybe a hot tub, or maybe at work you've had to test the pH of like different like cleaning solutions. But you take the little strip of paper, you dip it in whatever solution you have, and then you compare that color to the scale. And so like this one kind of looks maybe like 6, maybe a little 6 or 7. And so then you'd be like, okay, so what does that mean? Well, for pH, acids, pH is less than 7. And what that means is you have a lot of H pluses. Because remember, let me go back here really quick. Remember, pH is based on the negative log of the H plus. So if you have a lot of H's, it's a low pH. All right, so let me get back here. So pH less than 7 is considered acid, because that means you have a lot of H pluses. If you have kind of the same amount of H's and OH's, then that pH is right around 7. And then if you have a base, then the pH is greater than 7, because that means you don't have very many H's. Instead, you have a lot of OH's. So that's the idea. So then what I would do is I would say, oh, well, this looks kind of like a 6, maybe between 6 and 7. So it'd be close to neutral, maybe not perfectly neutral, but that would be the idea. Oh, and then if I had like this one looks kind of like a 2, so that would tell me, oh, this is acidic. And then this one that looks kind of like darker, that's maybe like a 9 or a 10. Oh, okay, that's a base. And then that could be useful to know if I'm cleaning something, or if I know whether or not it's safe to touch, that pH could help me. All right, so go ahead and do a level 3 kind of question, a predict, a defend, that kind of thing. So now think about, and then just process what we did today. So we know the definitions, the properties of acids and bases, and then we know a little bit about how we measure acids and bases related to the molarity of the H pluses and the OH minus. And then we have this pH scale that quickly helps me see acids, neutrals, and bases. All right, that brings us to the end of the first day of this new unit on acids and bases. Go back and finish any COSTA questions, write your summary for today, and then again, if you're watching these video notes as part of class, you have an Unit 11 plan that shows you what we're going to do each day. It has the objectives that you should be learning each day. put that into your notability so that you can follow along. And then there's Unit 11, unit practice problems. Do them, helps you process these new notes. Did they make sense? Check your answers to help you see, did you learn what you were supposed to learn? All right, thanks so much for listening and learning more about acids and bases. We'll see you next time.